So here is another question on properties of electromagnetic waves. So it is given that the electric field in an electromagnetic wave is given by E is equal to 50 sine 2 pi by lambda Ct minus x Newton per Coulomb. Find the energy contained in a cylindrical cross section of area 10 centimeter square and length 50 centimeter along the x-axis. Okay, so before we solve the question, we will actually just pay a little attention to this expression of electric field, which is 50 sine 2 pi by lambda Ct minus kx. Okay, this much Newton per Coulomb. It can also be expressed in volts per meter. It will be the same thing. Okay, so now let us try to understand this. So here, if we do this 2 pi by lambda into c, we can write it as 2 pi by lambda into lambda by t, because c is the speed of electromagnetic wave. Okay, that is equal to how much? Wavelength by time period. This, so that's we have written here lambda by t. C we have expressed as lambda by t. So here lambda gets cancelled, so we are left with 2 pi by t, capital T, time period, which can be written as 2 pi f, because reciprocal of time period is equal to frequency, which is equal to omega, which is the angular frequency in radian per second. So here this 2 pi by lambda into Ct, it is basically omega t. And also remember, 2 pi by lambda is nothing but the wave number k. So here this is Ct minus x. Okay, Ct minus x. This is not kx, Ct minus x. This one. This is Ct minus x. Just x here. Let me. Okay, this is Ct minus x. This is x only. So here 2 pi by lambda, when it gets multiplied with x, 2 pi by lambda into x, that is basically kx. So this expression is basically, it can be written as 50 sine omega t minus kx, that format, omega t minus kx. So as I have discussed it many times, basically you will find these kind of representations: omega t minus kx. In some cases it will be kx minus omega t. In some cases you will have cos. Okay, sine. These things will change: sine omega t minus kx, sine kx minus omega t, cos omega t minus kx, cos kx minus omega t. So these variations will be there. It does not make a difference. Okay, so this thing is clear. Now let us come back to the question. I just wanted to make you understand that. Now it is given that we have to find the energy contained in the cylinder. So as you can see from the equation or the expression of the electric component, the propagation direction is along x-axis. Okay, the propagation direction is along x-axis. That's why it is given. We have to find the energy contained in an imaginary cylinder of cross-sectional area 10 centimeter square and length 50 centimeter along the x-axis. So if we draw the visual representation, okay, here nothing has been mentioned about in which axis the electric and magnetic fields they are oscillating. So here let us say the electric field is oscillating along the y-axis. Let's say nothing has been given, so let us say the electric field is oscillating along the y-axis like this. So here we have is an imaginary cylinder, okay, an imaginary cylinder along the x-axis with a cross-sectional area, okay, this is the imaginary cylinder with cross-sectional area. How much? It is given 10 centimeters square and a length of 50 centimeter along the x-axis. So we have to determine the energy content of that. So here we have to use the concept of average energy density of an electromagnetic wave. So it can be expressed in two ways. First, using the electric component, and then using the magnetic component. So here we'll be using the electric component, that thing which is expressed as 1 by 2 epsilon 0 E0 square, where epsilon 0 is the absolute permittivity of the medium, E0, capital E0, that is the amplitude of the electromagnetic wave, the electric component of the electromagnetic wave. So here from the question, the amplitude E0, that is equal to this much, 50 Newton per Coulomb or volt per meter. This is the amplitude, peak amplitude of the electric component of the electromagnetic wave. So here, okay, so here it will be equal to 1 by 2 into 0.5 to 10 to the power minus 12, that is the absolute permittivity, into 50 square. So that is equal to, it is coming 1.1 into 10 to the power minus 8 joule per meter cube. This is the average energy density of the electromagnetic wave expressed in terms of the electric component. Now here the volume of this cylinder, okay, the volume of this cylinder, that is equal to area into length, which is equal to 10 centimeter square into 50 centimeter, which is equal to 500 centimeter cube, which is equal to 500 into 10 to the power minus 4 sorry, 500 into this much 10 to the power minus 2 whole cube, that is equal to, it is coming 5 into 10 to the power minus 4 meter cube, expressed in terms of meters. This is the volume. So the total energy content of this cylinder will be equal to the total energy content, that is equal to the average energy density multiplied with the volume of the cylinder. So that is equal to 1.1 into 10 to the power minus 8 joule per meter cube multiplied with 5 into 10 to the power minus 4 meter cube. That is equal to, it is coming around, okay, 5.5 into 10 to the power minus 12 joules. Okay, 1.1 into 5, 5.5, 10 to the power minus 10 to the power minus 12. Okay, 5.5 into 10 to the power minus 12 joules. So this is the energy content of this imaginary cylinder of cross-sectional area 10 centimeter square, length 50 centimeter, along the x-axis for an electromagnetic wave with its electric component expressed in terms of this equation. Okay, so this is the thing. And here is an interesting way of representing the same component, electric component, in different ways, but essentially it will either be in omega t minus kx or kx minus omega t format, in some cases sine, in some cases cos. Okay, so this is the thing.